So hi everybody, my name is Gallagher Pryor. I'm going to be leading through a presentation today on AccelerEyes Jacket and how it pertains to medical imaging or medical image segmentation. Just as a quick note to everybody, we're using the integrated audio of WebEx, so you need headphones or speakers to listen to me, and then of course a microphone to plug into your computer if you wish to speak. I'm going to try to monitor the chat window as well as we go through here so I can answer questions. But with all that out of the way, let's go ahead and jump into the presentation. So the outline for today is that we're going to introduce Jacket from MATLAB and then go into exactly what makes that tick. And then we're going to talk about the G4 feature of Jacket. Then we're going to compare with a PCT alternative and show how Jacket is far more advanced and faster than PCT and provides greater value. And we'll talk about moving into the future with our ArrayFire products. But then, with all that aside, we're going to get into medical image segmentation towards the end. We'll look at some code, see what it takes to take segmentation code and run it on the GPU, and then do a benchmark to see how fast Jacket really is in comparison to a very hefty CPU. So the best way to get a handle on Jacket is to look at some code. So what I have here is a simple 6-line example of how we can estimate pi using Monte Carlo method. And what we're doing here is we are sampling 20 million points on the unit square using the grand command, which creates random numbers on the GPU. And then taking those numbers and computing their distance to the origin and finding out how many of those are inside the circle, as we see here on the side, and then the ratio, how many fall inside the circle versus how many didn't, is used to compute the value of pi. It's important to notice that we're using grand here. This is all that's needed to go ahead and get this algorithm on the GPU. And to take a sidestep here, the way you interact with Jacket inside MATLAB is through the 6 major data types that we now provide: G-double, G-logical, G-uint, G-int, and G-single. So with these data types, you cast your data over to these new data types, and then all the following commands on those pieces of data run on the GPU. These are in the data types that we provide work exactly like MATLAB arrays. So you can work with vectors, you can work with matrices, you can also work with volumes, and everything works exactly the way it does as CPU variables do. You can even do subscripted referencing, subscripted assignment using the colon operators to pull out slices of volumes, to pull out rows of matrices, and also you can use ends just like you can in MATLAB so that you can easily manipulate arrays. And then once we've created the data on the GPU, jumping back to our code, once we've created the data on the GPU, all this following code where we compute the distance to the origin, compute how many points fell inside the quarter circle, all that's run on the GPU since everything was instantiated from grand up here, which results in a G-single. And that's in a nutshell pretty much how you work with Jacket to get CPU acceleration within MATLAB. Just the beautiful thing here is that no GPU-specific stuff is involved. You don't have to write any kernels. There's no threads. There's no blocking. It's just regular M code. All the arrays work exactly the way they do as they do on the CPU. And then your code just hopefully, unless something goes horribly wrong, just works. And a little quote here. Very little recoding was needed to promote our lattice Boltzmann model code to run on the GPU, Dr. Kevin Tubbs from HPTI. So real people have gotten acceleration out of their codes with Jacket. So I wanted to go in and talk about a little bit about G4. This is where Jacket departs from MATLAB, and it's very, very powerful. So the best way to get a handle on what G4 is to go through a couple examples. So the top example I have here is a for loop that does 3 matrix multiplications serially. This is very simple. And if this were to run on the GPU using Jacket, just in the form that it is here, there would be 3 separate kernel launches in order to accomplish what you wanted to do. If you run it in a G4 loop, however, what G4 does is it says, all right, the following operations in the body of the loop are going to be executed in quote-unquote batch mode. So there will be only one kernel dispatch for this entire operation. The way to think about this is that here up top, this original for loop is doing the iteration 1, iteration 2, iteration 3, computing all the matrix multiplies in our 3 kernel launches. Whereas in the G4 case, you can think of G4s extending these matrices out into the 3rd dimension, into the next dimension, does all these iterations all at once. So you can picture them as doing 3 matrix multiplications all in one go, as shown in the bottom, or even as taking the inputs to this matrix multiply as a volume times a vector, and then resulting in a volume. It's a volume behind the scenes, but to you, it looks like just 3 matrices, and it's a very, very powerful construct. I'll hopefully get to talk about that later on when we get into the segmentation examples and how it can aid you. So the other way to think of G4 as syntactic sugar. It really adds another dimension to MATLAB code so that you can write more vectorized code, or vectorized code in an iterative fashion, instead of just in a vectorized form, which is a little complicated to wrap your head around sometimes. So Jacket extends easily to multi-GPU. So we make it really easy to use multi-GPU through our gselect command. Gselect, what it does is it selects a current GPU, the ICE GPU in this case, to be in context. It does some work with GRAN and FFT, and then it moves on to the next GPU. And the beautiful thing about this is that these 2 commands, GRAN and FFT, are non-blocking, meaning that as you gselect more and more GPUs, all this work is being queued up and then executing simultaneously on all the GPUs. So you can use multiple GPUs with Jacket without having to deal with threads or GPU context or any of that. You just gselect different GPUs and then run your code. So on a very, very high level, what Jacket offers is a full technology stack, a full system that's trying to make optimization for you. There's a memory manager within Jacket. There's code that handles binary handling, the GPU multiplexing that I just talked about. A lot of computation that happens within Jacket is JITted, which means that custom kernels are compiled on the fly and then run to get your job done. And then there's also, we have several heavyweight functions like ML_divide, in-dimensional convolution, and find, which are highly tuned CUDA binaries that can run, and these are all very, very nicely tuned to run on your code. So a lot of people get real results with Jacket, from neuroimaging to Georgia Tech to power engineering in India, video processing at Google, to bioinformatics at Leibniz University, from anywhere from 17x speedup to 70x speedup. So just to compare quickly with the MATLAB PCT product, so when we're working with the GPU, there's not only memory between that sits with the CPU and memory that sits with the GPU. There's not only that boundary, but there's also a boundary between the GPU cores and GPU memory. And it turns out that there's 300 cycles one-way penalty for accessing global GPU memory. And what's going on when Jacket executes code is that it optimizes transfers between the CPU and the GPU using smart copy semantics, but it also attempts to minimize this transfer of data between GPU memory and GPU cores via this optimized runtime that I was talking about, this full technology stack. So if you were to look at the way PCT does things versus the way Jacket does things, PCT is going to do work here for the sign and then a plus and then a power all separately, whereas in Jacket they're all done together, relieving ourselves of this 300 cycle penalty over and over and over again as you execute commands. So as you can see, there's 634 cycles for Jacket versus 1,834 cycles for PCT, so we're well ahead of the game there. So theoretically, this is a 3x increase, but actually it's a 20x difference because PCT runs in a legacy Java system, and we just have better GPU code for Jacket. So Jacket also has 10x more functions than PCT. It's a huge amount of functions, which include reductions, dense linear algebra, gcompile for compiling M code into GPU code, convolutions, FFTs, and the list goes on. There's tons of functions out there, and we've gotten to the point now where we can run a huge amount of code with Jacket on the GPU, and also a huge amount of code within G4 on the GPU, which is very, very useful. And the bottom line at the end of the day is that if you write your code on top of Jacket, it's easy to maintain. So you can write your code once and then let Jacket carry you through the next hardware evolution. So for instance, back when Fermi came out, our users didn't have to go back and rewrite their code to use the new hardware. They just had to get a new version of Jacket, and that let them take full advantage of Fermi without having to worry about any code rewrites. And the same thing will happen with Kepler when it comes out. So one of the exciting developments that we have is moving Jacket into C, C++, Fortran, and Python. We can now execute. We have the same code that exists in Jacket runs inside C, C++, Fortran, and Python. So you can write your code in MATLAB and then easily port it to C and C++. Okay. Now I want to talk about medical image segmentation. Just want to give a simple example. So in this particular presentation, we're interested in the segmentation of grayscale images. In particular, this brain slice image that we show here. So on the left-hand side, we have the raw image, and on the right-hand side, we have a resulting segmentation that comes from a Bayesian segmentation algorithm that I'll explain in a little bit. So the Bayesian method, the overall goal is to segment a volume into n classes. And for the examples that we're going to see a 2D example of segmentation, and we're also going to see a 3D example of segmentation. And the idea is to create n data terms, guess it n prior terms, apply Bayes rule n times, and then find the maximum of the n resulting posteriors to determine the winning class, and apply a label for the winning class. So it's sort of like fitting multiple Gaussian models to some data, and then picking which pixel belongs to which class in the segmentation based upon maximum likelihood. And this was written up in the publication here, an ITK filter for Bayesian segmentation back in 2006. And the reason we picked this segmentation algorithm is because it's epically simple, and you'll see it in the code that we're about to see. So let me go ahead and pull up the code and jump into a MATLAB demo, and hopefully you'll be able to understand more of the algorithm. Here, actually, let me see if, no. Okay, no questions yet. So I'll just go ahead and I'll jump into the code. I'll look at the brain segmentation CPU version first. And let's see if the whole thing, yeah, pretty much the whole thing fits on one screen. So I'll jump through the code and explain how the algorithm works real quick. So the first thing we do is we load an image into memory. This is this brain slice that I showed in the presentation. And all we're doing is we're taking the mean of it to get it to grayscale and then dividing it by 255 so that all the image values are from 0 to 1. In the segmentation, we're interested in segmenting into 3 classes, and we start out with priors that are all uniform across the entire image. So this means that each pixel has it starts out with an equal probability of being in each segmentation class. So here I've actually done the normalization here by taking the sum over the third dimension of the priors and then dividing it through. We start out by saying, okay, our 3 classes are just going to be random variables. They're just 3 random means. Each Gaussian that we're going to work with has a standard deviation of just 1, which is really, really simple. I'm simplifying the model so the code is simple. Start out by computing the likelihoods in each class, and then we continue by computing the posteriors, multiplying by the likelihood, and setting the priors to the posteriors. And then we smooth the priors, and that's accomplished by a comp2. And then we normalize the priors once again so that the probabilities are normalized. And then we recompute the means that are computed here. And then we show the result. And I'm just going to go ahead and run this real quick. So here we're seeing the final posterior for each of the 3 classes. Let me run it multiple times. It selects different means every time, so the segmentation is always different. So I'm just segmenting over and over and over again. And these, you can see we've got one class for the background, one class for the brighter white matter, and then for the grayish areas we have a 3rd class. And this is decent segmentation. It's not the greatest, most high-tech thing in the world, but it just goes to show you know, what you can do with such a simple piece of code. Now with the simple piece of code, we'll show what this looks like on the GPU. And hopefully you'll be able to see what the differences are in the code pretty easily, and how we ported it to the GPU and how easy it was. So the first thing that happens is that on the GPU, on the left-hand side I have the GPU code, and on the right-hand side I have the CPU code. So on the GPU code, all I've done is taken the image that we loaded in and cast it to a G-single. And then whenever I'm using a generator like ones or zeros, or anything else like that, here's another zeros, I'm adding class I to the end to tell the generator I want to generate data that is of the class of I, which just happens to be G-single. So I cast I to a G-single up top, and then the class of I, which is the GPU data type, ends up just cascading down throughout the rest of the code, and the rest of the code runs on the GPU. So that's pretty simple. There weren't very many changes here to actually make this run on the GPU. So let me see if I can run the GPU version of this real quick, just to show you what it looks like. It looks a little different, but same sort of results. I'll run this several times so that people can see it. It's a little hard to see the GPU version because it runs so fast. There you go. There you have it. So there's the GPU running the same code, just with casting data. We're able to run it on the CPU. So just out of curiosity, let's see how fast the CPU is. So it's 4.78 seconds for the CPU to run. See how fast the GPU is. So just on this simple code where it didn't do hardly any optimization, it didn't touch G4 or anything else like that, we saw that the CPU was able to run in 4.78 seconds, whereas the GPU was able to run in 1.52 seconds. So already there's a speed up just by casting data over to the CPU or to the GPU. We also have a 3D version that can segment volumes using the Bayesian algorithm. I'm going to show that real quick. I'm not going to get into the code because it's more complex since it's 3D. So here we have, we're taking slices through an MRI, and we're just segmenting them over and over and over and over again. It's doing the whole volume each time, but we're just going through slices for ease of visualization and to point across how fast this is moving. And it's running at 1 step per second, so that's one segmentation of the entire volume per second. Okay. Let me run the CPU or the GPU version. Oh dear. There it goes. It was sitting behind everything. I wonder why that was. Anyway, you can see here that this is running at 16 frames per second, which means being able to segment the whole thing at 16 times a second. And in the same way that we're doing convolutions in the 2D example, we're doing convolutions as well in the three dimensions, so that's conv n. Let me run that again. So this conv n is actually the bottleneck here in this example because we're just moving over a 3D volume. Okay. So getting back to the presentation, I have one picture that I want to show. So here's some across-the-board benchmarks of commands that get used. So the bigger ones, so conv2 in Jacket is up to 52 times faster than conv2 on an i920 Nehalem versus a Tesla C2050. So on the huge image sizes and the huge chunks of data for conv2, you really get a benefit with using Jacket. For regular convolution, it's 17x. That's just 1D convolution. And for 3D convolution, as you saw, it was easily 16x. We could bench that, and I'm sure it would go. The speed up would go up. So with that, that ends the presentation. I hope that was interesting and helpful. And I'd like to open up the floor to any QA or questions. So I'm going to open up the chat window here. Okay, so one question is, can you use Jacket for active contour segmentation? So you can use, so you could probably use Jacket for active contour type segmentation. The key operations there would be convolution, most likely to maintain a signed distance field and to evolve a surface. So I think that probably Jacket would be very useful in trying to do an active contour segmentation. Oh, I got a question. So is the brain segmentation available in Jacket? Yes, it is. So everything that I showed except the 2D brain segmentation, which probably should be an example in Jacket, is there in Jacket. So you can see exactly how the 3D brain segmentation example works. So what other image processing examples are there in Jacket? Okay. Let's go take a look, actually. I can actually go through the list of examples here. So all our examples included with Jacket are in the examples folder of the install. So there's brain segmentation, which I just showed. There's a convolution example, which is interesting. There's a filter 2 example that's pretty interesting. So there is anything there. Interp 2 example. Jacket is a very, very fast interp 2. It has a very, very fast interp 2. And also there's an optical flow example. And also a volume rendering example. So here, I'll run the optical flow example and see if I can navigate to it over here. So here's a cool example of computing optical flow. This is just a horn-shunt PDE version of optical flow. And over here on the left-hand side, we've got some synthetic imagery of some point sources moving in and out from center of gravity. And here we have a quiver plot showing the flow field. So oops. There we go. Look, so I've got another question. While having data in the GPU, is it possible to do volume rendering? So it is possible to do volume rendering. So just to make sure I'm still got everything on the path. So we have a command called volume that you can hand cubical volumes to. Here's the example right here. So all I did there was create a 32 by 32 by 32 block of data, and I just passed it to volume, and here's what that random data looks like. So for medical imaging, let's see, where am I? We have a volume example that actually displays a brain, hopefully. There we go. Let me make this smaller so that you can see it. But here we have volume rendering of a cranium, and it is completely interactive. You can zoom in and out of it and see your data in 3D. So that answers that question. We do have volume rendering. So I got another interesting question. So it says, if I read the code correctly, changing I equals G single I to I single I, or simply commenting that I equals G single I would result in the code running on the CPU. Was that the only difference? The answer is there was a minor point that I skipped over there. I'm glad you asked that question. And now I'm out of the correct directory. Let me get back to the directory that I want to be in. Yeah. So there are actually a couple differences. So if I were to take the G out from here, the rest of the code should run on the CPU. The only difference being that we'd have to turn off the GPU-specific graphics commands. I forgot to talk about those. That's my bad. So if I turn off the graphics for the GPU and I remove the G from G single, and I run brain 2D GPU, this code will just run on the CPU. And then by putting all this stuff back, G single, and then G subplot, G subplot, G subplot, G color map, saving it, and then running it. Oops. Yeah, we have the GPU version back. Oops. Did I run the wrong one? Yeah, there we go. There we go. Yeah. So the end answer to that question is that yeah. So as far as the compute goes, just switching out G single to single gives you the CPU version back. You just have to watch out with graphics because the graphics don't exactly have a CPU equivalent. So you need to remove those G subplots and the G color map. But otherwise, it just runs on the CPU. So it's not like you're taking your whole code and twisting it around to get the answer that you want. So I have another question. We want to do edge detection for object tracking. Do you plan to support this? So the answer to that is edge detection is already supported in Jacket. You can test that out by running it real quick. Yep, there we go. Well, there's edge detection on a random chunk of data. A good place to go and check this out at is our wiki. So actually, I ought to show that to everybody. So go to wiki.accelereyes.com, and down here I can always search for a command like edge, and then I'll get whether or not it's supported in Jacket or not. So here are all the supported syntaxes. There are actually a lot of supported syntaxes. And there's also links to the data types these things are supported on. So unfortunately, we don't yet support canny edge detection, but that's in the works. And we do intend to support canny edge detection pretty soon. So are there any other questions? Okay, well, anyway, I'd like to thank everybody for attending. This is fun, getting to mess with Jacket online. And it's cool always sharing demos and looking at code. So I hope that this is informative, and I'd like to thank you for your time.